a new version of a rather traditional soil climate simulation model called the Newhall Simulation Model, which we now updated it to run in Java, so we call it the JAVA Newhall Simulation Model. But before I just tell you a little bit about myself, for those who have not met me or have not yet met them, I have a master's degree in soil genesis and morphology from Penn State. I have about 28 years of experience in soil survey, and about the last 20 of those spent working with the National Soil Survey Center and also working with simulation modelers who use our data. And much of my current work deals with gridded SSURGO and making our data readily accessible to modelers. And in the past, I've served as data steward for national products like dominant soil orders and suborders that was published with soil taxonomy in 1999, major land resource areas of the United States, and also helped publish the SSURGO data twice, in 1994 and also in 2006. There, I told you a little bit about myself, but I want to tell you something that I'm not, and one of those things that I'm not is an expert in soil climate. And I do not wish to suggest that I am in this presentation today. However, I have learned an awful lot about weather station records and soil climate model assumptions during the development of this JAVA Newhall Simulation Model software. This is prepared in joint cooperation with the Penn State Center for Environmental Informatics, and I was the manager of the Cooperative Ecological Studies Unit agreement on that. So I will defer to Dr. West and others at the National Soil Survey Center staff that have far more experience and expertise in soil taxonomy than I do, but I'll give it a shot. So this afternoon, Dr. West and I hope to share a little background on the origins of this model. They've been with us since the late 20th century, and how to operate the software and apply it in a climate study. We will use the Mammoth Cave National Park as our climate study, case study. And first, a few observations about climate. Climate is a major driving force of soil processes and behavior properties in the past and in the present, and as we anticipate the future. Climate's been treated as static in soil classification and soil survey. It is a difficult topic to handle, given various issues with resolution, scale, time, mesoscale processes versus microclimate. Currently, soil taxonomy assumes that there is a normal year and a normal distribution of climate years in precip. The JAVA Newhall Simulation Model provides a systematic and quantitative approach to characterizing soil climate regimes. It can provide clues about more variable soil landscapes and trends through time, can help recognize rain shadows and defining climate criteria and ecological site description. Climate graphs and various climate calendars that we'll share with you represent soil processes through the calendar year. Numbers of leaching events, or the intensity of leaching, transportation of clay, periods of drying and clay deposition, vernal pool and playa behavior, and provide a description of weathering environments. As such, perhaps these could be attached typifying head-on. And just to get started here, a quick primer or review of soil temperature regime basics. Many of you probably work in a couple of different soil temperature regimes. I've just put them up here. From left to right, we go from cold to hot with the delic or permafrost, cryo, frigid, mesothermic, and hyperthermic in the red end, the right-hand side there. We also have ISO versions of these. And just for a little history on soil taxonomy, back in 1975 when this model was constructed, the definitions were a bit different. I think there was a less than 5-degree difference between the summer and winter soil temperatures at that time, and I believe that was changed to 6 degrees in 1999. All right, and here a little review on soil moisture regimes as well. We have the aqueous moisture regime, which is really defined by morphological characteristics, presence of reductomorphic features. So it's really not dealt with in this soil climate simulation model, so I'll mention that. From top to bottom, we go from the wettest soil climate regime of per unit, where precip exceeds ET in all months in most years, and the soil moisture control profile is always moist. Then we go to UDIC. Uptick, we get progressively drier to xeric, we form a Mediterranean style climate until the desert acidic moisture regime, where often the soil moisture control profile is never moist. For those who are interested, as you begin to run the model, you're going to find a few new old terms that are presented to you by the model. Under the moisture subgroup modifier box, we'll find a group of proposed subdivisions to the traditional soil taxonomy moisture regime. For example, here in the UDIC, you see pre-UDIC and pre-UDIC are basically the same. Left-hand side are the proposed subdivisions by Dr. Armand van Wambeke of Cornell University back in 1982 when he was doing some USAID work funded by USDA. And on the right-hand side are our conventional moisture regimes from soil taxonomy. UDIC, however, is subdivided into two, typic UDIC and dry temp UDIC. USDIC has three divisions, wet tempustic, typic tempustic, and xeric tempustic, each becoming progressively drier. And xeric has two, typic xeric and dry xeric. Aritic has three, the weak, typic, and extreme. And just for a little background for you all, I've included some high points on the definitions of what these new proposed soil terms are for reference. The appendices of the user's guide gives a detailed explanation and the definitions of these. All right, and now I'm going to hand this over to Dr. Larry West, and he's going to talk to you a little bit about some of the Newhall assumptions, especially those dealing with the way that moisture is managed throughout the simulation in the moisture control section.
Thanks, Sharon. Sharon said, I guess, John said, I'm the National Leader for Soil Survey Research and Laboratory. I'm a guru on soil climate either, but I'm probably almost the only person in this audience that used the old basic version of the Newhall model back actually in the 80s. So I played with it a little bit over time. And my piece of this is, models shouldn't be treated as black boxes. So I'm going to give you a little overview of kind of how the model operates. It's all in the user guide and the associated articles at the back and da-da-da-da if you're interested. You can also check to see if I screw it up. As Sharon said, this model was actually developed by a person named Dr. Franklin Newhall, who was a USDA employee. It was published in 1972. This is not a new model. It's also not a sophisticated simulation of water movement through soil. It was developed to calculate soil moisture regimes for soil taxonomy. So there's not a lot of sophistication to the mathematics or anything else associated with it. It works, though. As you use this, you need to remember that the soil is essentially regarded as a sponge. It is a reservoir with fixed capacity. So it's a sponge in a bathtub. The default, it's all based on the available water holding capacity of the soil profile. The default value is 200 millimeters, and we'll talk more about that in a minute. That value, the original model, it was fixed. You can change it now. Water is added to the soil by precipitation. It's removed by evapotranspiration. The other thing to remember is when the bucket's full, you can't put any more water in it. When the water holding capacity is satisfied, if you get additional water added, it disappears. The assumption is it's runoff or leaching, and we're not talking about which one it might be. In terms of temperature calculations, the calculations for soil temperature regimes are based on on an offset from the mean annual air temperature. The default is 2.5 degrees C. Again, you can vary that if you have additional data that says it should be something different. So the soil in the model is represented as a matrix of 8 by 8 boxes. An 8 by 8 matrix of boxes, 64 boxes. Each row of that matrix holds 1/8 of the total available water holding capacity you specify. Each box holds a 64th of that available water holding capacity. The relationship between available water holding capacity and depth is something that I don't think I've got my mind totally wrapped around yet. The basis is available water holding capacity. Each row has 12.5% of the total available water holding capacity. It's not a depth. It kind of is if you want to look at it that way. The ones closer to the top are more shallow, the deeper ones, but there is no fixed depth. It's a variable depth. The soil fills from the top. That would make sense. It empties with slants, as they call it in the model documentation. In other words, it doesn't empty from the top, it empties on a diagonal. It's based on the energy required to remove water, which is a function of both the matrix potential or tension and the depth of the box. And I'll show you some examples as to why I'm on. So, wait, let me back up. I went too far. So as you add moisture, it adds from the top. If you think of this box, the water content increases from left to right, or tension decreases from left to right, whichever way you want to think of it. So you have precipitation. It will fill the first row before it begins to fill the second row. And then it will continue in order until the bucket's full. Now, when you deplete soil moisture, like I said, it's on slants, and the order of depletion of boxes are 1, 2, 3, 4, 5, 6, 7, 8, 9, so forth, to where the lower left-hand corner is the last box emptied. The representation on the right is a representation of energy that's based on a potential evapotranspiration equivalent that they derived. So you'll notice the 5 boxes in the upper right-hand corner have a potential of 1. So 1 millimeter of PET results in 1 millimeter of water loss. The lower left is a 5, which means it takes 5 millimeters of PET to get rid of 1 millimeter of water out of that box. And in between, those number varies is based on some logarithmic progression that they don't specify, and I didn't take the time to try to figure out what it was exactly. So water is added and water is depleted. That's kind of the take-home message. The other thing, we haven't talked a lot about the soil moisture control section, and I think most of you are familiar. It's the depth. If you take 2.5 centimeters of water and add it to a dry soil, it's the depth that water penetrates in 24 hours. It's the top. You add, 8 centimeters, 7.5 centimeters, 3 inches of water to a dry soil. It's the depth that water will penetrate in 48 hours. It's represented in the model as 2 rows, the second and third row of cells, for the area that's cross-hatched. So if you want to think about depleting soil moisture and as the model works, we start, this one's totally full, and if you think about some of the definitions in soil taxonomy, you can just say it's moist in all parts of the moisture control section. It's all wet. You start drying, and you see it's drying by slants, And now the moisture control section is dry in some parts of the moisture control section. If you continue the process here, we've eventually worked in this whole soil's pretty dry. We only got a little water left in it. We start re-wetting. Again, from the top, you notice this doesn't change. But now we're back to moist, and my figure got screwed up somewhere. This should be blue all the way across. Sorry about that. Should be moist in all parts of the control section. Hopefully you get the concept. It varies it. And it's kind of an interesting way it does it. You should read that and think about it. Let's talk a minute about available water holding capacity, or if you've dealt with laboratory data sheets, it's called water retention difference there. They're equivalent, kind of. Well, they are equivalent. As I said, the default is 200 millimeters. What does that mean? So if you say you have 200 millimeters of water in a 200 centimeter soil profile, that means that every centimeter has 1/10 of a centimeter of water. If you think about texture and the effect of texture on water holding capacity, a lot of times people will use sandy loam. They'll say we'll have about 1/10 of a centimeter per centimeter of water retention. Now, if you talk about, say, 80 millimeters of available water holding capacity for the profile, and you're still talking about a 200 centimeter profile, now it's 0.04 centimeters per centimeter. In other words, much less ability to retain water, and maybe that's something like a sand. So you can get some concepts from texture. Now, if it's a shallow soil, 50 centimeters of hard rock, we use the same 200 millimeters, now it becomes 4/10 of a millimeter, 4/10 of a centimeter per centimeter, or 4 millimeters per centimeter. There aren't any textures, mineral textures, that hold that much water. Organics maybe, but no mineral textures. You go to an 80 millimeters of available water, maybe it's 0.16, something maybe like a loam or a clay loam or something like that. Now, if you're going to use the model and you want to think about this, those data are available for all the soils for which bulk density clods were collected at the time of sampling. It's called water retention difference. On the data sheet, it's right out beside bulk density. I've got two soils here that I took from the database. One is a Memphis. If you're not familiar with Memphis, what is it? It's a fine, loamy, thermic, I don't know if it's mixed or silicious, typic-acudol. It's a nice, silty, low-silver-derived soil. Occurs in western Tennessee and Mississippi. Pardon? Oh, it's fine, silty. Thank you. Wrong one. The other one is a Conlin, and I don't know that soil. I've never seen it. It's a coarse, loamy something. I didn't even look up the classification. It was just a data sheet that I got to that had some numbers that I liked. So if you look at the Memphis, the silt loam, silty clay loam, all the way through to 2 meters, water retention difference varies between 0.22 and 0.26 centimeters per centimeter. The Conlin is more variable in texture, and the water retention difference varies between 0.1 and 0.17. Now remember, you can't add centimeter per centimeter values. You have to multiply by thickness. So if you take the horizon thickness times the water retention difference, you come up with the available water holding capacity for the horizon. So for the AP, it's 22 centimeters thick times the water retention difference. You have to multiply by 10 to get from centimeters to millimeters. Pay attention to your units. They'll tell you every time. So that's 57 millimeters. You go through that exercise and add it up. And the 2 meters, this soil has a water storage capacity or water retention capacity of 480 millimeters. Remember, the default's 200. So if you're working in thick, lush landscapes, you might want to think about what that default is, what you put in for that value. On the other side of the fence here, if you're worried, the other soil came out to 265, which is pretty close to the default. Now, if your soil is shallow, if you only took that to, what's 19, it's 11, 43 centimeters of the Memphis, so you had hard rock at 43 centimeters, the available water holding capacity would be 99 millimeters. So, and the point is, you need to think about the dominant condition in the area you're trying to mimic, model the moisture regime. If you got a bunch of shallow soils, you want a low water holding capacity. If they're nice, thick, silty, lurchal soils, maybe you want more than 200. Because that's going to make a difference in the model outcomes. This is an annual calendar of moisture conditions in the control section. This is a model output. You'll see this in the model output. 30 days per month. The top row is January. The bottom row is December. To give you an idea. This is using climate data for Lincoln, Nebraska. So if I say it has 80 millimeters of water holding capacity, you'll notice that there's a pretty appreciable period where the control section is either dry in some parts or dry in all parts. Actually this is August and September as the period of the year that it occurs. And it's still UDIC, but it's on the dry side of UDIC. It actually qualifies for the dry temp UDIC piece. If I use 200 millimeters of available water holding capacity, same climate data, everything else is the same, it's clearly unique. So it will vary depending on that. So it is an important thing to think about. Just don't use the default and expect to get the right answer in all cases. And I think, Sharon, it's your turn.
Okay, thank you, Larry. I think it is my turn. All right, well, I'm going to talk to you a little bit about the development of the Java version of this kind of traditional Newhall simulation model. And just a few highlights here. Again, I mentioned before it was done through a CESU agreement with Penn State. And I think we did that work principally in 2009, 2011. And I also want to acknowledge all of the NRCS and cooperators who helped us review, especially some of the folks from Cornell who were working at that time in the early 90s and 2000s who helped provide information that was not easy to find. It is based on the 1991 Wambeke Basic Code. It reflects the soil taxonomy rules at that time and also includes proposed moisture regime subdivision terms. And if you would like to see a simulation of what that moisture addition and depletion would look like, we have posted a YouTube video on the background page of the JAVA Newhall Simulation Model web pages. Go to soils.usda.gov, and I'll show you later about that. And it really helps you better understand what the model is doing there. It is a Java application. It has got a Flex wrapper on it that handles all of the user interface inputs and output data from the model. And it provides identical results to the 1991 code if you provide the same identical inputs. We did add a summer and annual water balance calculation and also an interactive user interface where you can actually key in a single year's worth of data if you happen to just have that kind of information from your own field study. It also provides large batch runs, and that's perhaps its greatest strength at the moment, your input data. We use standardized input and output parameters, which was a little archaic from the original work. We've documented these in a dictionary. You'll find them in the user's guide. Input is a simple, comma-separated variable file. or CSV, and it can be created easily using an Excel template. We provide those too. The output is stored in an XML format and can be converted back to a CSV for easy manipulation in tabular form. With this update, we've increased the speed of the model going from about 3 minutes in a DOS-Box emulator to about 25 milliseconds. So it's all over almost before you click the go button. We took the software and had it GCE through USDA this year, and we deployed it to NRCS desktops this month. I think it started last Friday, and according to my sources, I understand about 1,428 installs have occurred. I'm not quite sure exactly what that means, but that's what I've been told. Okay, let's talk about its requirements. This is a monthly step kind of model. It's really considered more like a mesoscale model. It's really pretty appropriate for regional assessments and so forth. It requires serially complete monthly precipitation and air temperature for a calendar year or years from a weather station. And by serially complete, we usually say between 20 and 25 days of the month should be reporting in to consider that you've got a reasonable estimate of what's going on in that month for either air temperature or precipitation. Weather station metadata, we need the name, the station code, what network it falls within, the location of it, and the start and the end year. We also record elevation, but that's just most of the metadata information. Also requires, as Larry explained, an available water capacity value computed for the soil profile that is at the weather station or nearby. Sometimes we call that value the AWS value, available water storage, within the profile too. We also need what we call the mean annual soil temperature minus mean annual air temperature offset value. And this is an important consideration because this is how the model estimates the mean annual soil temperature. It bases it right off the mean annual air temperature. We'll talk about this in the tutorial, but we can get this from the SCAN data or from the literature where others have done research. We also include user metadata. And then finally, inputs must, and I can't emphasize this enough, must all share a common unit of system of units. For example, when we get climate data, sometimes it comes to us in English units, non-SI, like in degrees Fahrenheit or inches of AWC or inches of precipitation. And sometimes it comes to us in metric or SI units like degrees centigrade or millimeters of available water capacity or millimeters of precipitation. And occasionally it comes in mixed units, so that's why Larry mentioned too, we have to be very mindful of the units in our data preparation and as well as our analysis. All right, getting started. This is a pretty modest software development project, so we basically simply took the old 1991 code and packaged it up and made it a lot easier to access and use in a modern computing environment. As such, there's no online help or things like that, but we have developed quite a very nice user's guide, and we've created a soils website devoted to the Newhall model. You'll find this on the soils.usda.gov webpage, and you'll find some quick links on the soil classification pages right here over on the left-hand side. Oops, maybe you won't see that. jNSM-soil climate model. We'll get you there. So there's a background piece. That's where you can find that little YouTube video. There's the user's guide, which I'll review with you here shortly. There's also the public software download, and there's a bundle that includes everything, sample data sets, the user's guide, all software and so forth for our cooperators or any other public user. We also include sample templates, which you can download here, and some example weather station Excel and CSV files for running through. We also provide some sample output. And we also provide links to various sources for the soil climate information sources, which include our Soil Climate Analysis Network as the National Water and Climate Center, United States Historical Climatology Network, and various NOAA regional climate centers like the High Plains Regional Climate Center has some excellent information there, as well as the Northeast Regional Climate Center, which we use in the study we'll talk about shortly. And with that, we'll go to the next slide. And also, just a little reminder, the little icon here to the right is what the JAVA Newhall model will look like. Those of you who have received it on your desktop through a CCE deployment the software is already installed on your computer. If you find that you can't locate it, you go to all programs, you're going to see something called JAVA Newhall Model, something like that, JAVA Newhall, and you can request it through your TSC or ITS person that you have it manually installed if you wish to request it. A note about data management. Because this is an independent piece of software, it lends itself to people's files going crazy with the way they manage their data. So I've suggested here a little template and now organization of how to keep your data organized so you can find it yourself the second time through, as well as sharing it with others. Basically, you'll see here I've set up a folder called Java and then add the project name to it. And then I would set up one of these for each of the projects you wish to do, and then include in it some of the reference information so you can always go back to fresh information like blank template input. And that will include your Excel files as well as your CSV file. Output. This is where your XML and then the CSVs that you can generate from them can be stored. It also keeps the README text on file. It gives you the full complement of everything within the original bundle, and the user guide we're ready to use. All right, now I'm going to switch gears a little bit and take you through the user's guide, which is very well written by Jim Sloan from the Center of Environmental Informatics. And I think I am going to share a program. And let's see how it loads here. Might be a little delay here. The Newhall model, when you download the user's guide, that is, for the 1.5.1 version, looks like this. It's a simple little guide, and it's the first about a dozen pages are devoted to the model, and the second half of it is really devoted to the content. So I'd like to review with you two here just a short note about the background, how to run the application once it's installed on your system, and then a little bit about the appendices for what the batch input mode format looks like, and the XML output, and then the useful references. Again, it's just as we've reviewed here a little bit before about Franklin Newhall and his efforts. I believe Dr. Robert Grossman used to tell me as a young scientist he was asked to compile a lot of the climate data that Dr. Newhall needed. So that was a very interesting little note there. Running the Newhall application, let's take a look. The little icon you see, whoops, it'll take just a moment. Is that refreshing shot on your screen?
Short answer is no.
Oh,
Here it just
okay.
started, didn't it? It's going.
Yeah. I think I might just stop with this next one, and I'm going to go straight to the demonstration or back to the PowerPoint. Yeah. I guess I would invite all of you folks to look at the PDF in detail there, but mainly the important thing to know is that you can run the model in an interactive mode, or you can run it in the batch mode. At this point, I think I'm going to switch over to the, okay. If I hope this looks the model itself, and we'll just go from there. All right. You should see the JAVA Newhall screen interface online right now. So what we have here is there's an input mode tab at the top and an output. And then the second tier of tabs are data and user information. So it's a very simple interface. You get your little turned around once in a while. But I'd like to go through and just review a result of the model run right now. So we choose out a single model run, and I'm going to go to my output. Here, project name, output, and look at a sample data set from Williamsport, Pennsylvania from the year 1930. All right, so up comes, quite straightforward here. You'll see you're in a single model run, select the model file, and we're looking at the input file. The XML itself will contain both the input parameters as well as the output parameters, so you can reconsider the model runs you've done so you can make sure you remember what inputs were considered as well as the results you received. So here we say the station name is Williamsport, Pennsylvania. We have the metadata related to elevation, latitude, longitude, station ID, the beginning year, and the ending year. It also was originally done in English units. All output are stored in metric units, however. Below here, you can see there's an air soil offset place, and we say the original model run was 2.2 degrees Fahrenheit. Water holding capacity was 7.9 inches. Below, you'll see the mean monthly precipitation in inches and the mean monthly air temperature in degrees Fahrenheit. And note, we see gaps filled by interpolation of neighboring stations. Sometimes when you need to run long-term records, you have to help fill in some gaps in order to make a month or two usable to salvage a year. Let's look at the output you get then. There are 3 kinds of reports that come up. The first one I clicked on was actually the metadata report. I'd like to start with the first report, which is called the climate calendar report. Looks a lot like the graphic that Larry shared with you a moment ago. Here we see at the top you have the metadata information repeated again. It's for a single year. Period is 1930 to 1930 calendar year. And this case, the mean annual precip was 703 millimeters. Moisture regime is classed as uptick, which is unusual for that part of the world, north central Pennsylvania. And the temperature regime is mesic, and here's that unusual term. It's a wet temp uptick, so it's kind of wet on the wet uptick side of things. We can take a look here. The output gives you a mean annual air temperature, mean annual precip, all in metric, and then the modeled estimate of the monthly total potential evapotranspiration in millimeters, as well as the modeled estimate of the monthly total water balance. The last column shows the annual values for those as well. The soil temperature calendar shows you when blue indicates, again, each row is represented by a month, and each of the columns is a day in the month. We have 30-day month and a 360-day year in this model. Blue is when soil temperatures are less than 5 degrees C. The tan is when they're between 5 and 8 degrees C. And the green areas are where they're greater than 8 degrees centigrade. To the right on the soil moisture calendar, dry is indicated by red. The moist dry color is tan, and moist is indicated by green. You can see later in the year there it's like it stopped raining for that part of the world. The next report we provide is something called a climograph. And on the y-axis we have the precipitation and potential evapotranspiration given in millimeters. And across the x we have a calendar year with monthly data points identified starting in January, ending in December. Again, we have repeated the metadata information and the classification as a result of the model run. At the bottom there is a small legend. We have the blue line with 2 little circles at the end that indicates the precipitation with the data point. If you interact with the model, you'll see that the precipitation value will actually appear. You can find out if you want to just check the model. The same goes for the potential evapotranspiration. If you do that on the curve that's red, you'll find whatever those values are as well. Under the curve, the surplus is indicated by the blue fill, and then the pink color is shown by what we call utilization, or where potential evapotranspiration elevation exceeds precip. Things are pumping out more than we have there. So where they overlap together is the purple area in between. But the utilization peak is indicated by the pale orange or red color. And then the last portion, as I might mention in the lower right-hand corner, these can all be saved out as PDF for each individual model run that it contains the data at the time of the run and so forth. The model run summary here is kind of that little metadata information, and it includes user metadata as well as the station that you are running and all of the inputs so you can double check yourself. This is all embodied in an XML file. Something I failed to mention here, I'll mention it now. On the input tab, before the user begins to use the model, you're asked to enter your user contact information. So each individual person can have their personal model run. So here, if I wish to change my email address or something, I can make an edit to it, I can submit it, and then it's preserved, so it will be updated for all future model runs. So that's what I have on the model run for the moment right now. We do have a short tutorial too to head through, and I'll see if how far I can go with that. Alrighty. Alright. This is a little case study we pulled together. My co-authors here are Pete Bigham, who's our Soils Program Coordinator with the National Park Service in Lakewood, Colorado, and William Waltman, who's a research associate here at the West Virginia University. And Bill has probably about the most experience with the Newhall model that I know of. I think MLRA has worked with an older version than we did back in the early 90s at Cornell. So let's go through this quickly. I think we identified about 10 steps that most people should consider when we're thinking about conducting a soil climate study, especially one where you might want to apply the Newhall model. First step is write a hypothesis about the climate regime study that you're about to embark on. In our case, that the soil climate regime is Udic and the temperature regime was Mesic. Second step, review the literature. Find out as much as you can about that area. You have wonderful digital resources online too. Identify all of your data sources and say weather station data that were available in neighboring individual years or summary of years within your MLRA study and your neighboring MLRA. In our case, we have a study in MLRA 120A, which is the Kentucky, Indiana, Sandstone, Shale Hills Valley Southern part. Some of those sources are the SCAN source I mentioned before. We use some work data from the Northeast Regional Climate Center, and also there's the U.S. Historical Climatology Network, too. You can prepare that offset between soil temperature and air temperature from your SCAN data. You're fortunate. Pete recommended using this national park because there was a SCAN site located there, and we have very good data for that site. I'll make a note. Using the 1 or 2 year data logger studies are useful information, but they can be a little misleading if you don't have enough long-term records to figure out what's going on. Once you assemble your data, you really need to go ahead and prepare your input Newhall table. Run the model, examine the results and compare with neighboring stations, analyze your yearly climate probabilities, and generate moisture and temperature regime frequencies for the study area through time. Review any anomalies or outlier years for impact of natural events such as hurricanes, degraded tropical storms, droughts, etc. And finally, identify any long-term trends or patterns in the data. Here is a little summary of the climate sources we chose and a timeline. Across the bottom, you'll see we start in about 1870 on the left-hand side and go to the present. Well, we actually go out to 2020 out there with a 10-year increment. The best climate records in the Historical Climate Network usually start about 1895 and go through the present. That's shown by the red bar there. And for our site, there was about 117 years of information available. The next best length of record was the supply log data source, which is like a national, it's located at Cornell University, and we're able to download monthly information from there. That was for 78 years, starting in 1934. Most of our analysis, I'll show you, is dealing with that. And then the tiniest, the smallest record is the Soil Climate Analysis Network, or SCAN network, which was, we had good records from 2004 through 2011. And there's also, across the bottom, you see little sunbursts that are red with a yellow center, and these are little areas of drought events that we compiled together from the National Drought Mitigation Center's record. You can see how they come and go across that timeline. There's also a pink line there between 1955 and 1974 that comes out of an article from Minnesota that talks about periods of benign climate, or times in the climate records when the climate seems to have settled down and be very stable. I want to show you some of our results. Here's the scan information. Scan sites are often co-located with other weather stations and also monitor soil temperature and moisture. So if you can't find full records on the scan site, you might be able to go to neighboring sites to help. Usually scan sites have less than 30 years worth of records. And the National Weather and Climate Center also provides the traditional task and wet tables for 30-year normals that can be used to provide input data for the Newhall. Historically, the task tables with their 30-year normal values were served as the input for the JAVA Newhall Simulation Model. I want to go back just one step here to the log. I failed to show that we have one other, the orange bar here at the bottom from 1971 to 2000 is a summarized value of 30 years worth of monthly information from 1971 to 2000 from the Northwest National Weather Service Co-optation. And we provided one of our sample data sets includes the national collection of those weather stations for the nation on the website. Here's what it looks like for the scan site, and in particular the site for Mammoth Cave. And you see what the scan site looks like. When downloading scan data, it's suggested the settings are, that you use for downloading the data are highlighted in blue here on the screen. And I think you will get the calendar year for 2011 if you download for this one here. You need to choose all sensors, no chart for a full suite of information, and need to download daily values 1 year at a time, and then summarize monthly values for the Newhall. The soil head-on report is the click points of that shown by the red arrow. You can download and obtain the information that you need for calculating the available water capacity that Larry described. For our site, we used that information and came up with either 6 inches or 153 millimeters. Again, be careful not to mix English and SI units when we are dealing with the scan data. Next slide is a little sample of the download here, the CSV file that you get, and got the T average is the average air temperature in degrees C, and SDO is the soil temperature in degrees C at a 20-inch depth, actually 50 centimeters, if you want to stick strictly to unified units. So be careful of the mixture between English and metric there. A few other items in working with scan data. Maybe some of you are familiar with that already, maybe some are not. Be careful with the scan end of the hydrologic year duplicate record. There's the -999. It's highlighted in orange here. So you need to delete that when you get going there. And just move on here. Let's take a look. Here is the calendar year for 2011. And we're looking here at daily air and soil temperatures at Mammoth Cave. Let's take a look at some of this. We take some of those data and plot them by year with depth in the soil profile in centimeters here. Note that the maximum here, I think the average is kind of shown in the purple curve. It's the composite, I guess. It's 2004 to 2011. And blue and red are cooler years from 2008 and 2011. Note that the maximum actually occurs at about 20 centimeters, which is about the bottom of the cloud layer. And also that soil taxonomy uses the 50 centimeter depth here, and you'll see the mesothermic threshold here, 15 degrees C, that our temperature values are on the thermic side for most of that time. Here's an example of where we compare the mean annual air temperature and the mean annual soil temperature. Soil temperature is given in the red line, higher, mean annual air temperature in blue, and here we are in degrees Fahrenheit. The average offset here is about 3.6 degrees Fahrenheit, or about 2 degrees C, and that served as our source for our runoff model input. Here's a summary slide where we have actually shown how that's computed in the upper section. So here's the offset from the years 2004 through 2011. And below, we've looked at the neighboring scan sites that had reasonable data. Note the period of records vary. And we have offsets that vary from about 1.6 degrees C at the Shenandoah, Virginia, to 3.7 degrees C at Fort Assiniboine in Montana. So these usually vary regionally, so there's no one answer that's the silver bullet to an offset value here, but requires regional understanding and knowledge. Other sources is just the Regional Climate Center here. They have lots of good data that's earlier, older records available. Each of the regional groups should be consulted as their site. Here's an example of what the Excel files look like for the JAVA Newhall input file for that 1934 to 2000 record. You can see here the first record is the 1934 highlighted in red, and at the bottom we've kind of skipped a few records there and gone all the way down to 2011. You can also see here where we've indicated AWC was in 6 inches, mean annual air temperature, soil temperature offset was 3.6 degrees 6. We started with an English template and ran these as English input units. Here's what it looks like when we can take a look at the longer-term records. Here we're going from about 1934 to 2011. We've added the offset to just mean annual air temperature and look to ask what the soil temperature does through time for each of those years. Across the bottom we have the decades, and on the y-axis we have degrees Fahrenheit for the mean annual soil temperature. You can see that an awful lot of the time we are almost over the thermic area there. And there does, if you look at the dotted trend line, it looks like we are on an increasing rate there. Also note here we've tried to kind of put in this little period of benign climate from the mid-50s through the early 70s. Kind of looks like there's low amplitude here, kind of settled down a little bit compared to some of the wilder extremes that followed before or after. So here we are. The Climate record scan offset values were used as inputs for the JAVA Newhall, and we ran those 78 years. So based on the model results, frequencies of soil moisture and climate regimes were summarized for this climate record. We did that for each of the 78 years, and then we computed the probabilities. We looked at the number of years and the percent frequency during this period of time that the temperature regime shifts from the hypothesized Mesic Utic regime. The site is 58% Typic Utic, 23% dry temp Utic, 7% wet temp Utic, and 3% xeric. The site is also about 14% Mesic and 64% thermic for the same period. The 10 non-Utic years were either eustic or xeric, and thought to be indicators of drought events. Here we are back at our timeline again, and if we take a look at those events, here the little starburst now is orange for ustic years, pink for xeric years. So 1936, 45, 1952 were all uptick years. 1953 was xeric. 1963 was uptick. 68 all swell. 1983 went xeric. And 1999 went xeric. And then we had 2 more events for uptick in 2007 and 8. So we'll take a look at what the 1999 xeric record looks like here. Here is the 1999 record for the climate calendar report. And we can see here it's thermic, xeric, typic, xeric. And you can see here the number of days of dry or moist dry in the moisture control section. If we look at the climate graph, you can see that the precip here is much lower than we might anticipate. And then if we compare this with the average of all of those 78 years together into a long-term record, and kind of average out all that range and variation, it will come out to a yimbic, thermic, typic-utic kind of a classification. Here we see the precipitation in the blue line is much higher than we would think it would be, and the utilization in this region is much smaller. And here, if we go back to the 1971 to 2000, 30-year normal record, which is in the sample data set we gave you, you can see that that one does come out as thermic, utic, typic-utic, and you can see in the moisture calendar it's completely moist on here. This is what the climograph looks like for that same record on 1971 to 2000. So summary and conclusion. The Newhall model is adapted for mesoscale modeling of soil climate regimes with limited data, can be used with PRISM data sets, and I have just a little slide here I'll share with you on that too in a moment, or with TAPS or wetland tables from the National Water Climate Center, or with Historic Climate Network. And it's also applicable for modeling in national parks, across MLRAs, other wildlife refuges, and so forth. You can also use your own monitored soil climate information if you are an avid soil climate person in the field with your soil survey. From NAVA, a couple of parameters for soil climate can be derived. These include the annual water balance, summer water balance. By the way, these are all in the user's guide and detailed in the appendices for you. Growing season water balance, biological windows at 5 and 8 degrees C, and frequency of events, often helping to build drought stories when we have these events in time. It handles local, regional, air, soil temperature offsets, and root zone available water and cooling capacity conditions. Trade-off is that it relies on a less robust EEC approach. It's a thermal versus a biophysical. It uses the forest waste method. But it has broader geospatial applicability to remote areas with geostations or limited sensor data. And it helps us to better understand the polyclimatic character of a soil landscape and how climate-driven processes, soil processes can behave in time. Now with that, I have just one quick other slide to share with you about how we might begin to take a model that we've shown here just to run on point data at weather station sites and how we might begin to apply it in a geospatial sense. We can, using the PRISM data, gather monthly precipitation and air temperature information and construct for each cell, I think this is 800 by 800 meters, an input record to go into the Newhall model. We're working with some of the researchers at National Soil Survey Center, Dr. Zamir Lubahova and Edwin Winsler at Purdue, and Dr. Philip Owen and others here at West Virginia University. And we've been able to run the model at that resolution that's about 12 million pixels across the lower 48 states. And we have some preliminary results. Here we're looking at the Bowling Green Airport weather station, which we're looking at the theme that's being shown on the GIS screen is summer water balance. And it's kind of in the kind of more yellowy, kind of blue range there that corresponds with about the summer water balance that we found at the weather station 2. We were using as our input parameter for available water and a mass unit average for the state soil use, or the digital general traditional type of analysis here we're talking about. It'll be a really good backstop to help us on some of our harmonization or soil data joint correlation efforts to give us a good context and setting for that kind of work. So this work is still in review, and we hope maybe later this year we might have some of that information to share as well. And with that, I think we are done. Thank you for your time.
All right, and so now we'll open it up to some questions, and again, that'll be by the Q&A. And I've received a few questions already, so I'll start with the ones that I have and let people enter their questions in that Q&A tab at the top of the live meeting screen, and we'll take them from there. So the first question I have is, will Sharon's presentation be available on the jNSM website? Good reference material. So yes, I think that's a good idea. Of course, all of our webinars are archived on our webinars, presentations, and training sessions website. But I think providing a link also on that jNSM website is a good idea, so we'll link it to both places. Then there was a question for Sharon. You mentioned that in 1975, the original ISO regime was defined by a 5-degree difference in mean summer and mean winter temps, and was changed in 1999 to 6 degrees. Do you know why? Why was what was the reason for the change from 5 degrees to 6 degrees?
Well, actually, I commented on was not a good person to answer that question. I was just reporting when we found all the rule changes.
Yeah, so Joe Schrader to come up so he can talk into the microphone here.
That change happened with the second edition of Soil Taxonomy in 1999, and it was simply a clarification of an inconsistency in the first edition. The difference between the ISO temperature regimes was defined as less than 5 degrees C difference between the mean winter and mean summer temperatures. And in the non-ISO temperature regimes were defined as more than 5. Well, that doesn't work very well when you actually try to apply temperature in whole numbers. You cannot use temperature in fractional values. It has to be in whole numbers. So the correction was that the ISO regimes are less than 6, and the non-ISO regimes are 6 or more. So that difference defines the, for instance, the difference between mesic and isomesic has to be less than 6 to be an isomesic regime. So it was simply a correction to the first edition. We really didn't change anything except to clarify what the actual limit is.
All right. The next question.
I'll make sure the figure gets updated too to make sure it's correct here.
The next question comes from the West. How does the model take into account slope, aspect, and curvature?
How does it take into account slope aspect and curvature? Actually, I don't think that it does. I think the model assumes kind of a weather station setting. And when we were working with some of the prism data, that prism data has an aspect, an orographic factor already factored into it, so we work with it that way for large areas. I think there have been others, and I know that both Bill Walton and myself and Tim Prescott and others actually did some work where we did terrain regressions based on the point data, where we got at aspects and slope and elevation, latitudinal differences and things as well. But the model itself is not. I think it does take into account latitude and longitude for identifying the proper hemisphere, though. The VET model does. I don't know if that's helping or not.
My next question is, have soil data collected at NRI sample sites been used for soil climate simulation modeling and regional assessments?
Well, that may be a good question for some of the SEEP and EPIC modelers. Do we know? Maybe Larry might have a little better insight into that. I'm not aware.
I think short answer is no.
I think it's a good idea, though. I think especially if we have actual AWC type information or good estimates of it at this point.
Okay. we'll move on to the next one. How are rock fragments addressed in terms of AWC for the profile in this model?
How are rock fragments addressed?
Right.
Okay, I believe, and Larry will hopefully back me up, both in the water retention difference as well as the AWC that we report and calculate as available water storage are already rock fragment corrected. So those have already been subtracted from that total in millimeters, diluted in effect for the rock fragment content.
And another question, or a comment anyway, there is another model being developed, EPIC, similar to jNSM. Can both models be used for the same classification, and how would this work?
That's a really good question. I think both Larry and I should probably answer. I think that this is an historic model, pretty much, and it's used for the basis of a lot of our early classification assumptions. And it would be great to have some kind of correlation with a more precise daily time step model like EPIC.
I agree, Sharon, and that's in the works. I think that model will be available probably by the end of the summer. EPIC's a lot more input data intensive. And like Sharon said, it's a daily time step. The water movement simulation, the heat transfer, all of that good stuff is also in there. So for a few sites, you get really good information, but to get a lot of sites, it'll take a lot of work to assemble that information.
All right, and with that, I think I need to bring our webinar to a close. I want to thank everybody for your time and attention. And again, this recording will be put on our archive webpage online and linked to the jNSM website. Thanks all.
Thank you.